So I will speak today about the control and stabilization of partial differential equation system when there is an essential term, which is a quadratic term. So the outline of the talk is here. So first I will speak about the controllability of this type of system, and then we are going to move to the stabilization of this system, and we'll present two methods to stabilize this type of systems. But let us start with the controllability issue and some examples. So there will be the examples which are coming from the KDV control system, a KDV control system introduced by Lionel Rosier. And then I will speak about the water tank control system introduced by Pierre Rouchon. And then I will show some prior obstruction. And finally, I will conclude by giving the main ideas for the obstruction to small time local controllability for the KDV equation. So what is the KDV equation that we are going to consider? It's a system which is used to model the height of the water inside the channel, which was invented by, which was found by Boussinesq first, and then also by Korteweg and De Vries. And this is equation 1. So you have the derivative of y with respect to time, yt, plus yx, the derivative of y with respect to x, plus y triple x, plus a quadratic term, which is going to be important in this talk, yx equals 0. So this is inside the channel. So x is between 0 and L. And on the boundary, you have the directly boundary condition. Yt0 is equal to ytl, which is equal to 0. And the control is the Neumann boundary condition at x equal 1. That is yxtl is u of t, which is the control. So the state is in L2 of 0L, for example, and the control is u of t, which is in R. So this system was introduced by Lionel in 1997, Lionel Rosier, and he first gives some very important results. He studies the controllability of the linearized system, so you around 0. So you forget the quadratic term, which is yx, and you arrive to the control system, which is 2. So yt plus yx plus y triple x equals 0. This is inside the domain, and on the boundary you have the directly boundary condition, and yxtl is the control is u of t. And then he proves this very interesting result that you have the controllability of this linear system if and only if, in fact, L does not belong to this set N, which is defined by 3. And moreover, he proved in the case where L is a critical length, that is, L belongs to N, then the uncontrollable part is a linear space, which is, of course, always the case, but it is of finite dimension. And this linear space, we are going to denote it capital M later on. So now we want to move to the controllability of the nonlinear system. And we are going to give some definition. What is a small time? What is a local controllability in time t? So you have around 0. So you have 0, and you say that you have the local controllability in time t if whatever is a red ball. So this is a ball in L2. There is a smaller ball, a ball in L2 again, such that if you have two states in the small ball, the blue ball, then it's possible to find a control which is small, it's less than epsilon, which allows you to go from 0 to capital T. This is a notion of local controllability in time t, and if you have this notion, whatever is t, we are going to say that the system is small time locally controllable. And with this definition, there is a result due to Lionel Rosier, which tells you that whatever is capital T, the KDV control system is locally controllable, the nonlinear system is locally controllable in time t if L is not a critical length. And this controllability is for the L2 norm for the state and the L2 norm for the control. And this type of property, we are going to say that it's small time local controllability. Everything is small, the control is small, the states are small, and the time is also small. And now the next question is what happens if L is a critical length? So there was a first result that I proved with Trepo in 2004, that if the dimension of the part which is uncontrollable for the linear system is 1, then you have the controllability in small time. So you have the small time local controllability. And the dimension of M can be of dimension 1 for infinitely many L, in fact. For example, the first example is L equal to pi, but there are infinity many L such that the dimension of M is 1. And then there is a result due to Serpa and Trepo, who proves that for every L, so there is no condition on the dimension of M. Then there is a T, which is positive, such that the KDV control system is locally controllable around 0 in time T. So it's not small time controllability, but it's already a very interesting result. You have the controllability, at least locally, if the time is large enough. And the proof of these two results relies on the power expansion. You make the expansion of the control, the state, and what is interesting is that in the case of the dimension equal 1, you have to do the expansion up to the other 3. While for the other critical lengths, then usually the dimension, it's emphasized to consider the expansion to the other 2. And the fact that you use an expansion to the other 3 gives you that, in some sense, if you can move in some direction in capital M, then it's possible to move in the opposite direction. Then this is why when the dimension of M is equal to 1, then you have the small time local controllability. You have this small time local controllability because if you can enter in M, capital M, in some direction, you can do also the opposite. While this is, if the dimension is, if the expansion that you use is the order 2, then it's not going to work as we are going to see. So what is the open problem then is, do you have the small time local controllability if the dimension of M is larger than 1? So this is still open, but we have some results in this direction. This is a result that I got with Armand Koenig and Hymin Nguyen in 2022. So you have a critical length, so L is given by 5, and you assume that 2 times k plus L is not a multiple of 3. For example, if you consider L equal to pi, that is k and L are equal to 1, then 2 times k plus L is a multiple of 3. But we are going to assume that it's not a multiple of 3. And then we prove that you have the obstruction to the small time local controllability, but it's not in the space that is natural for, that is L2 for the state and L2 for the control. It's for different spaces. The state is in H3 intersected with H10, and the control is in H1. So this is also a natural space for this type of equation because it's well posed for this type of equation, and you can prove also that if the length is not critical, then you have the small time local controllability for the nonlinear system. But then if the length is critical, but with 2k plus L, which is not a multiple of 3, then you do not have the small time local controllability in these spaces, while using the Serpa and Trepo, it's possible to prove that you have this large time local controllability. So, but it's still an open problem. That is it possible to get the obstruction for the state space is in L2, and the control is in L2 of 0L. And you have to be careful because the problem of the species are very important for this type of problem, as it was proved by Megan Bournousou in 2022. She got an example for a Schrödinger equation where you do not have the small time local controllability for some species, while you have the small time local controllability for some other species, which are the species are in the two cases they are natural. And I would like also to mention a nice result to Hymin and Nguyen, who got the good result in the sense that it's optimal for the species, for the KdV equation, but some other type of boundary condition. Yt0 is equal to Yxtl is equal to 0, and the control is Yt0. So there is still this open problem. Can we weaken the assumption? Because we have a positive result if the dimension of M is equal to 1. Our assumption is 2 times k plus L is not a multiple of 3, which implies that the dimension of M is larger than 1. But the interesting open problem is it sufficient to assume that the dimension of M is larger than 1 in order to get an obstruction to the small time local controllability? And also, in the case where you do not have the local controllability in small time, what is the optimal time to get the local controllability? This is also very important issue. And now we are going to move to the water tank control system. So later on, I will give some idea of the proof for this obstruction to small time local controllability, but I would like to present another example, which is the water tank control system. So it's a system which was introduced by Pierre Rouchon, which is a system which is very interesting for different application. You have a tank. Inside the tank there is some water, and the control is the force that you apply to the tank. That was in fact introduced by Dubois, Petit, and Rouchon in 1999. So the equation that is going, so the modelization is through the Saint-Venant equation. So in this model, you assume that the points which are on the same vertical has almost the same horizontal velocity, which is denoted by v of t and x. And you have the position of the tank, the height of the water at t and x. Then the equation is, you have two equations inside the domain. The first one is a conservation of mass. The second one is a conservation of momentum. And you have the boundary condition. I should have mentioned that the speed is the speed with respect to the tank. So on the boundary, the speed is 0. Vt0 is equal to Vtl is equal to 0. T is the position of the tank. So d dot is the speed of the tank, and s dot is the acceleration of the tank. So it's not the force, but you can do a change of variable, and you can. This is the same problem. You can take for the control, you can take the acceleration of the tank or take the force applied to the tank. This is the same issue. And you are interested in the controllability of the system. So first, of course, the quantity of water which is inside the domain is not going to change. So you have some quantity which is conserved, which is the integral from 0 to L of h of t and x. And also, you have that on the boundary, hx of t0 has to be equal to hx of tl. So the natural state space is the space which is given is this definition. And we are going to work with C1 regularity. You can also work with some other regularity. And HE is the height of the water at the equilibrium. That is when the water is flat. The level of the water is horizontal. Then it's possible that to prove that if the time is large enough, you have the local controllability of this system. And the question is, what can we say about the time? First, that was, I would like to mention that it was proved by Dubois, Petit, and Rouchon in this paper that the linearized control system around the equilibrium, which is just YE, the HE, H is equal to HE, P is 0, D is, for example, 0, S is 0. And they prove that the linearized control system is not controllable, but you see with the theorem that I proved in 2002 that the nonlinear term gives the controllability. And also they prove that you have the steady state controllability of the linearized system around YE, which is this, I'm going to show you what is this controllability that you want to study. You start with the tank, which is at some position, the water is at rest, the level is horizontal, and you want to move to the new state, and the new state is the tank has moved a little bit. T1 can be very small, but it's not zero. And the speed is again zero. The water is again at rest, and the height of the water is constant. So this is, you have two states, and you want to know if there is a control which allows you to move from the first state to the second one. If D1 is maybe very small, but not zero. And Dubois, Petit, and Rochon prove that it is possible to do this motion if the time is strictly larger than the critical time, which is given by the square root of L times HE divided by G. So the natural question is, can we do the same for the nonlinear term with the nonlinear term? And the answer is no. With Armand-Koenig and Oemin and Nguyen in 2023, we prove that if the time is less than 2 times the time which was found by Dubois, Petit, and Rochon, then it's not possible to do this motion for the nonlinear system. For the nonlinear system, you need more time to do this motion. Then it is a case where the nonlinear term is not helping. The nonlinear term, in the KTV equation, the nonlinear term gives the controllability, for example, and also the controllability was a water term control system. But if you want to do some specific motion, which are quite natural, then you need more time for the nonlinear system than for the linear system. There were prior obstructions to small time local controllability for partial differential equation. I should have mentioned that this problem of small time local controllability has been much studied, but in the case of finite dimensional control system, I will give some references later on. But for PDE, it's a very recent subject. So this is first, another example, this is a quantum box. It's related in some sense to the water tank control system, but now in the tank, in some sense, you have a quantum particle instead of water. So you have this quantum box, which is between the two red lines, and you have the wave function of the Schrödinger equation, the solution of the Schrödinger equation, and the control is the motion of the box. And for example, if you look for local null controllability, you may require that you start around the first eigenvalue. Is it possible to arrive exactly to the first eigenvalue with the position of the box, which is also fixed, and the speed is 0, for example? You can also look to the problem of the motion of the box. This is the same as the water control system. The box has moved, but the wave function is the solution of the Schrödinger equation inside is like at rest. It's equal to pi1 multiplied by expansion minus I lambda 1 t. Pi1 is the first eigenvalue. Lambda 1 is the first eigenvalue, and phi1 is the first eigenfunction. And you can also look for global controllability. Is it possible to go from the first eigenvalue to the second eigenvalue, for example? And there are some results, which they are given on this slide. But we are going to speak only on the first part, the steady state motion of the box. If you look for the linearized control system, you can, around the first eigenvalue, you can make it in small time. While for the nonlinear system, you need more time. You need some positive time. There is some obstruction to make it in small time. And so this is like for the water tank control system. For the nonlinear system, you get a result which is not as good for the linearized system. You need more time for the nonlinear system than for the linearized system. And the proof, I want to give you some idea of the proof. So you have the modelization. D is the position of the box. Psi is the solution of the Schrödinger equation, and so the modelization is here. So you have the equation inside the domain, the boundary condition, psi t minus 1 is equal to psi t1, and also the position of the box, the motion of the box. And you want to prove that we start from phi 1, for example. So you have this psi 0 of x is equal to phi 1 of x. This is the first eigenvalue. And you assume that S, which is the speed of the box, is 0, and also the position of the box is 0. And you want to arrive to S of capital T has to be again to 0, and D of T, you want it to be not equal to 0. So in order to get the obstruction, you define this function theta, which is given by 8, and you look to the dynamics of theta. And you introduce some kind of Lyapunov function, but it does not have any sign. It's a function which is, in some sense, it's linear with respect to theta. It's going to take its value in C, but in fact, later on, you are going to take the real part of V. And so this is the definition of V, which is given on the top of the slide. And then you can compute that V of T has this form where V0 and V1 are given on the slide. And then if you do the estimate on V0 of T, it's very close to S of T. So you see the leading term is the integral from 0 to T of S of tau multiplied by S of tau squared d tau. So it has a sign. V1, then the extra term is going to be small. And you see that if you take the real part of V, it starts at 0, but if you do the motion, that is, if S of T is not identically equal to 0, then the real part is going to look like the integral of 0 from 0 to T of S of tau squared. So it has a sign. And the fact that it has a sign, well, is going to prevent you to get the small time local controllability. And this is the type of method that we are going to use, but of course it's much more complicated in the case of the KdV equation and in the case of the nonlinear control system, in the case of the water-time control system. And also like to mention that there is a nice result due to Frederick Marbach. It's on the Burger's equation with viscosity, so it's given by 12, yt minus yxx plus yyx is equal to u of t. The bound u of t is a control, but it's a constant. It's not a u of t and x, it's a u of t. There is only one control, which is this function, constant function depending on time and the directly boundary conditions. And he proves that you do not have the small time local controllability of this system, Burger system. And the proof relies on scaling. Using some scaling, he can replace minus yxx by minus epsilon yxx, where epsilon is going to be small. And then there is also some quadratic terms. And again, he proves that some quantity has a sign, while it should have not a sign if you have the small time local controllability. And there is a very interesting open problem on this Burger's equation. Is the control system 12? Is it locally null controllable if the time is large enough? It's very nice, a very interesting open problem. So we are going to move to the KdV equation, and I would like to say some few words about the novelty compared to what was done before. For the Schrödinger equation, I should have mentioned that in fact the proof can follow can follow the proof that the obstruction of small time local contrariety for finite dimensional control system. And compared to the result by Frederick Marbach, it's difficult to perform the change of time scale in order to have some epsilon in front of yxxx, because then you have the boundary layer which appears close to the boundary. For the case of the Burger's equation, it's possible to have some good estimates of this boundary layer, but for the KdV equation, it's a very challenging open problem. And moreover, the linear drift term of the linearized control system is not self-adjoint, it's not skew-adjoint, so the eigenvalue are more complicated, the eigenfunction also. So I would like to give some idea of the obstruction to small time local controllability for the KdV equation. So I will start with a very simple example, which is finite dimensional control system. So this is a system 13. We have y1 dot is equal to u, y2 dot is equal to y3, y3 dot is equal to minus y2 plus 2 times y1 u. So the state is of dimension 3, it has 3 components, y1, y2, and y3, while the control is of dimension 1, it's the real number u. If you consider the linearized system, it's a system 14, and you see that this system is not controllable because the y2, y3 part is not influenced by the control. And for this toy control system, in order to get an obstruction to a small time local controllability, you can do explicit computation. You compute the solution of this equation for the nonlinear system, and you get the formula 15 and 16. And the two formula are interesting. If you look to 15, maybe you can see that if the time is less than pi divided by 2, then y2 of capital T is going to be larger than 0. You start from 0. It's a y2 of capital T. If the capital T is less than pi divided by 2, the cosine is going to be positive, and you get the estimate, you get this inequality. While for the second equation, you get something interesting. If you want to arrive with y1 of capital T equal to 0, so let's assume that y1 of capital T is equal to 0, then y3 of capital T has a sign not only for capital T is less than pi divided by 2, but in fact for capital T less than pi. So it gives you a better obstruction. The second property, the 16, the equality 16 gives you a better obstruction because it gives you that you have an obstruction to small time controllability if the time is less or equal than pi. And it's optimal, in fact, because you can prove that if the time is larger than pi, strictly larger than pi, then you have the small time local controllability. You have the local controllability in time t. And also, we need to do some perturbation of this system. If you have you see, with respect to some dilation, that is, for example, y1 and y2, you see, if you go back to the equation, you see that y1, in some sense, let's assume that the size is 1, size is epsilon, y2 and also u, then y3 and y2, the size is epsilon squared. So you have a different scaling. So if for this scaling you have a small perturbation, then you get some obstruction to small time local controllability by giving some better estimates than 17 and 18, which is given on this slide. You see now you have some quantification. Y2 of capital T, we know that it has to be positive or 0 if the time is less than pi divided by 2. And now you have a 19, which gives you a quantification of this inequality. And this is the same for 20. You have a quantification of the fact that y3 of capital T has to be less or equal than 0 if y1 of T is 0. And this is, in fact, 20 that we are going to use for the KDB equation. I would like to mention also that for this toy system, which is here, the fact that this system is not small time local controllability, not small time local controllative, relies, in fact, on obstructions which are classical, relying on iterated Lie bracket. This we use. You can use, for example, a condition due to Hector Sussman in 1983, and now we know much better obstructions which are due to Karin Bochard and Frédéric Marbach, and also Karin Bochard, Jérémy Leborgne, and Frédéric Marbach. Yeah. And Karin is going to give some lecture in this conference about this obstruction to small time local controllability for finite dimensional control system. But this obstruction rely on iterated Lie bracket, but iterated Lie bracket are not very well understood in the case of PDE controls, especially for boundary controls. And that would be very interesting to understand what is an iterated Lie bracket for control system modelized by partial differential equation. And for example, for the KDB equation, what are the Lie brackets in this setting? So we are going to use the same approach as for the local controllability, the positive result. So we do some expansion on U and also on the state, and we look to the equation satisfied by the expansion term. What is this, for example, what is the equation of y1? What is the equation of y2? and you get these two systems, 24 and 25. And in some sense, we are going to, what is how you prove the positive result, that if the controllability is, the time is large enough, or if time is positive in the case of dimension m is equal to 1, then the idea is to see if you can move for y1 from 0 to 0, but in such a way that for y2, you enter in M. And in fact, you want to arrive in a given, for any element in M, is it possible to reach any element in M by using a control U1 such that for y1 you go from 0 to 0, and for y2 you go from 0 to this element which is fixed in M. And for that, we use an expansion to the order 3 in the case of the dimension m is equal to 1. But also, I would have to mention that in the paper by in the three papers, we use contradiction arguments. We do not, so we are not able to really understand in which direction in M we can arrive, depending on the time. But now with the new approach, we first characterize all the controls which allows you to go from y1 equals 0 to y1 equals 0. So it gives you plenty of controls which allows you to go from 0 to 0 for y1. And if you use this control, what happens for y2? This is the question. If you start from 0 for y2, what is y2 of capital T inside M, if you project in M? So this is the main idea, the main novelty. Now we are going to describe all the controls U1, which allows you to go from 0 to 0 for the linearized system. And then we are going to study Y2 at time capital T. And we are going to see that if the time is too small, then Y2 of time capital T has to be in some explicit open half space if U1 is not 0. So it gives you obstruction to small time local controllability. So I'll just go quickly on this part, just to show you, there is no need to look in the details of on the slide. We just want to show you that the computations are not easy, but they are in some way rather explicit. So you consider the roots of the lambda of 26. You want to find the solution lambda, and you have three solutions, lambda 1, lambda 3, and lambda 3, which depends on z. And when you have these three lambda 1 number, you define Q, P, this, and finally we define this complex function. And it turns out that capital G and H are holomorphic. The other functions are not holomorphic, they depend on the choice of lambda 1, lambda 2, lambda 3, but G and H does not depend on the choice. If you exchange lambda 1 and lambda 2 and so on, you get the same function and you get something which is holomorphic. And so it allows you to give first the characterization of all the U, which allows you to go from 0 to 0 for the linearized control system. This is these two conditions. You consider that the Fourier transform, and the Fourier transform are such that by Leibniz, you have U at, this is the Fourier transform of U, and U at G divided by H are entire function, and also the Pan-Leibniz inequality, which is 32. So you have the characterization of all the U, which allows you to go from 0 to 0 in time capital T. And when you have that, you define this quantity, eta 1, eta 2, eta 3, and so on. And a key point is capital E. Capital E is given in 36. And this is a place where we use the fact that 2 times k plus L is not equal to 3. Because E is going to be not equal to 0 if and only if 2 times k plus L is not a multiple of 3. And then you define this function 38 psi of T and X, which is a solution of the KDV control system, which has a nice, so you see it's 0 if capital E is not 0, so we want to avoid that capital E is equal to 0 in order to have that psi is not 0. And you see it's a solution of the Nearest KdV equation, but it satisfies one more condition. You see, you have psi x t 0, which is equal to 0 also. And this psi here you really use this psi, which gives you the obstruction to the small time local controllability. Because you have this quantity, you have this inequality, which is given by 43. If the time is small enough, this time is small enough. You have this inequality. This is inequality for the solution of the linearized control system. But this inequality gives you an inequality for the solution y2. For the solution y2, which is defined by this property, which is given on the slide. And you have the y1 satisfies the inequalities that I have shown before, but the inequalities that I have shown before, the quantity which is the left on side of this inequality is exactly, in fact, the 50 is given exactly by 49. So you have this inequality 50 on y2, which shows you that you do not have the small time local controllability. That is, at least you cannot, y2 has some constraint. It has to be in some half space if the time t star is too small. But of course, now it's remains to take care of the, you see, we have made the quadratic approximation, but then you have to look to some, to the other terms, but it gives the result. It's not so easy, but you succeed to get so that if the time is too small, you have an obstruction to small time local controllability, which comes from this inequality 50. In the case of the water tone control system, the idea is roughly speaking the same. You look for the linearized system. So this is the equation 51. And then you have the expansion to the order 2, which gives you H2 and V2. And again, you have some property, you have some inequality, which has to be satisfied by H2 at time capital T and V2 at time capital T if the time is less than square root of I've taken the constant equal to, it's not T, capital T less than 2 with the physical constant, but it's capital T less than 2 times square root of L H E divided by G. And this inequality, then again, you can get that if the time is less than this critical time, then you do not have the small time local controllability. It's not possible to do this small motion, because H2 and V2 are going to be not equal to 0. So we do not arrive to the V, for example, and the H of the water is equal to HE, V is equal to 0, and the H of the water is HE. It's not possible to arrive to this state if you have moved a little bit. Now we are going to move to the stabilization issue. So in some sense, it's the same. Before that was a controllability of this control system, where the critical term is the quadratic term, and we want to do the same type of get the same type of result in the case where instead of studying the controllability, you want to study the stabilization, and then we want to find some methods which allows you to get the stabilization. For example, we go back to this example where you have this, and then you want to stabilize the equation. And you can try to do also for the water tone control system, there is the same problem. In fact, for the water tone control system, we are not able to do it for the moment being. So what is the phantom tracking? The idea is this: you have, I explained it on a finite dimensional control system. X dot is equal to f of x and u. and you assume that you have some equilibrium, x0, u0, let's take it equal to 0, 0. So f of 0, 0 is equal to 0. But you see, in principle, f of x and u equals 0. You have less equations than unknown, so you can expect that you have much more solutions than just 0, 0. You can expect that there is a curve, for example. Let's assume that the control is of size 1. You expect that you have a curve of equilibrium, that is f of x gamma, u gamma, is equal to 0, and when gamma tends to 0, it's converged to 0, 0. And then it may happen that you can stabilize x gamma, and then maybe it's better to explain it on the slide. You have the equilibrium, which is 0, 0. You have this curve of equilibria. And if you have an equilibria, you can stabilize equilibria. And the idea is to also move the equilibrium to 0, 0 in the same way, and using a feedback law, and then finally get the convergence to 0, 0. Let me explain that on a simple system. We take the same toy control system. Y1 dot is equal to u, y2 dot is equal to y3, y3 dot is equal to minus y2 plus 2 times y1u. So the state is of dimension 3, it's y1, y2, y3, and the control is of dimension 1. And you have some equilibria, which is 0, 0, 0 for the state, and the control is 0, but you can also consider u equal to gamma. Gamma is some real number, and then if you take y1 equal gamma and y2, y3 is equal to 0, you have a solution of f of y u equals 0, as you can see, because if you take gamma is the first component. If you take y3 and y3 is equal to 0, then you get that the second component f2 is 0, f3 is 0, and f1 is 0 because it does not. It's okay. So you have some equilibrium. Okay, you have some equilibrium. If you start from this point, use the control gamma, then you do not move. Okay. And then you could say, okay, I'm trying to stabilize this equilibrium, okay? And if you do the linearization of around this equilibrium, you get the system 2, okay? And then this system is controllable if gamma is not 0. So if gamma is not 0, you can stabilize the linearized control system, and so you can expect to stabilize the nonlinear system around this equilibrium. And then you move the equilibrium to 0. So this is what we do next. And for that, we can use Lyapunov function, Lyapunov approach. You want to stabilize gamma, 0, 0, 0. So we consider this function V gamma, which is minimal and equal to 0 at y1 equal gamma, y2 equals 0, and y3 is equal to 0. And you compute V dot. You compute V dot, and you see that it's given by equation 2. V dot is equal to 2 times u, y1 minus gamma, plus 2 times y1, y3. And then it suffices to take u, which is the opposite of this, of y1 minus gamma minus 2 times y1, y3. And so you get V dot is less or equal than 0. You cannot conclude by Lyapunov, but you can conclude by LaSalle. You use the LaSalle invariant principle, and you can show that that x, y1 is converging to gamma, y2 is converging to 0, y3 is converging to 0. And now you want to move gamma to 0, but you can make it in some implicit way. That is, instead of considering v, which is y1 minus gamma, you are going to put, for gamma, you are going to put v of y. So you see v of y is going to, y1 is going to converge to v of y, but v of y is going to converge to 0. So you are going to get that y1 is converging to 0, y2 is converging to 0, and y3 is converging to 0. And for this V, this is a V, you can find it explicitly, okay? You can find it explicitly because it's just a a quadratic equation. And then you can compute V dot. You get, you take this U, which is given on the slide, and you get that V dot is less or equal than 0. And again, you conclude by LaSalle. So there is some room for improvement. First, you can get a global result by taking this x1 instead of x1 minus v, you can take x1 minus theta of v of x squared plus x2 plus and so on. And sorry, there is no x4 square, where theta is well chosen. You can also get explicit feedback law by using an expansion, a dynamic expansion. You add some gamma dot is equal to v. And now you consider this phi and this w, and you can compute w dot and get that for explicit v and explicit u, you get the convergence to 0. So this method was used for the stabilization of the Euler equation for the incompressible fluid by Olivier Gass and myself. But that was used also for the quantum control system and the quantum box, for example, that I presented before, and also by Kamasa Holmes and Vincent Perolas. That would be interesting to apply this method to the water-tone control system. And if you consider if you take gamma, which is small but not 0, the equilibrium corresponds to the case where the velocity is 0, so that is V gamma is 0 in some sense, and H gamma, it's something which is linear, then the slope is equal to gamma. And if we look to the linearized control system around this equilibrium, we were able to prove that you can get the feedback law, a feedback law which allows you to get the convergence to 0. Okay, so now I would like to end up maybe with very quickly to some other method for which is we use stabilization and power series in order to construct implicit feedback law. So let me explain the idea on a very simple case. Again, finite dimensional control system. X dot is equal to X plus BU, and Y dot is L of Y. You can take L equals 0 if you want, plus Q of XX. So you see, if you do the linearized system, you get the equation 2. X dot is equal to AX plus BU, and Y dot is equal to LY. So it's not controllable. It's never controllable because you cannot change the dynamic of Y. And then you try to get the stabilization of this control system. And for that, we make some assumptions. So there is 3 assumptions. The first one is that if you consider just X dot equal to AX, then you have some exponential. In fact, you have the exponential stability of X dot is equal to AX. Okay, it's equivalent to the exponential stability. And that, in fact, you can, if you go back to the system, we are going to assume that the control system X dot is equal to AX plus BU is controllable. So you can always find the first feedback law in such a way that this assumption is for free, just by replacing U by AX plus V. Okay, so Q1 is just for free. The second assumption, often you get it for physical reasons. It tells you that if you consider just Y dot is equal to LY, it's not asymptotically stable, but it's in some sense it's stable. Okay, so you have this inequality that the norm of exponential t Ly is less or equal than 1. And then Q3 is more complicated to understand, but roughly speaking is this. You start, you consider equation 4. You consider 4. So you have a X tilde dot is equal to AX tilde plus B, V of TB. B is going to be on the sphere, SK minus 1. K is the size of Y. And you have the dynamics of x tilde, the dynamic of y tilde, and you start from 0. And you want that the V, which the V is open loop. V depends on the initial data. It depends on some B, in fact. It depends on B. But the V does not depend on X. It does not depend on the state, but it depends on some parameter B, which is in the sphere Sk-1. So if you use this V, and then if you start from 0, then X tilde arrives again at 0, and you have this inequality on Y tilde. Y tilde, the scalar product of Y tilde T dot exponential TLB is less or equals than minus delta for some delta, which is positive. So this is something that you can check for many systems. I'm going to give some examples later on. And then you have some explicit feedback law. The U that you are going to propose is given on the side, is given on Y. It's not very smooth. It's just Eulerian. The power is 1. The Eulerian coefficient is 1 divided by 2. And then if you use this feedback law, you get an exponential decay rate, which is given by 1 for some lambda, which is positive. So you have some exponential decay rate of not the norm of x, not the norm of x plus the norm of y, but the norm of x of t at the power 2 plus the norm of y of t, which is the natural scaling. That is, as we have seen before, y is like x squared. Okay, and you have this estimate. So you can do some perturbation again on as before for the local controllability, where we have this perturbation, and you assume that the perturbation satisfies this property. And then again, if you use the feedback that we have defined before, you get again this inequality for the exponential stability, but now the initial data has to be small enough. So this can be applied to many systems, which are very classical for finite dimensional control system. The baby stroller control system, the underactuate surface vessel system, for example, and also some systems that I have introduced to show that the necessary bucket condition for small time local for asymptotic stability can be improved a little bit. And it has been also applied for the KdV equation. For the KdV equation, now it's of course it's much more complicated because it is in infinite dimension, but we get this result. That is, so we assume that the length is not a multiple of 2 pi, and then the control system has a quadratic approximation expansion. We assume that then you can prove that there is some epsilon 0 which is positive, some C, some R, and some lambda, such that, and you can find the feedback law, such that if you have this, the closed loop system satisfy this inequality, and again you see that the scaling is the same. The uncontrollable part, the uncontrollable part for the linearized system, scale like the controllable part for the linearized system to the power 2, and we get this exponential stability. So let me just end by some open problems. A very challenging open problem. You see that we have shown that it's possible to get the exponential stability with some feedback law, which is not smooth in the sense it's just Eulerian, but the decay rate, the exponential decay rate, we are not able to prove that it can be arbitrarily large. That would be interesting to check if this is true. That is, you fix some number lambda, which is positive. Is it possible to get a U, which depends on time and Y, such that you get the exponential decay rate which is at least equal to lambda? It is also interesting to see if we can use a feedback law which does not depend on time. This is also an open problem. And finally, maybe the last open problem is it possible to adapt this strategy to the water tank control system? Okay, I'm going to stop here, and thank you very much for your attention.
So I have a question that regarding when you use the power series expansion method you mentioned, so that
Yes.
method works only if the missing direction space is in finite dimensional. But if that happens to be infinite dimensional, how you can approach this strategy?
Now, this is a very good question because I agree with you. We use the fact that it's a finite dimension because at some point we use the power fixed point theorem. So for that we need some compactness, and it's better to have a finite dimensional finite dimension. But on the other hand, it's not completely without hope because you can also try to avoid the use of this power fixed point theorem. And I think that was in fact done by for the case of the KdV equation but with the control I showed you before by Wyman and Nguyen, where you have this again, it's of finite dimension, the part which is not controllable for the linearized system, but he do not conclude, he proved, he has a new argument to prove that that you have the local controllability if the time is large enough without using the power fixed point theorem. So maybe this can be used for also for in the case where the dimension of the part which is not controllable for the linearized control system is sorry, I cannot find the, but this was for the other boundary conditions. The boundary conditions that I said ytl equals 0 and yxtl is equal to u of t. Yes, this is here. Yeah. Okay, yt0 is yxtl is equal to 0 and yt0 is equal to u of t. If I remember well, Wyman and Nguyen for the positive part, the small time local controllability, the local controllability is the time is not using the power fixed point theorem. He used something different. So maybe it can be useful for the case where the dimension of M is infinite. The dimension of M is infinite, for example, for the Euler equation. The Euler equation, the part that you can control by using the linearized control system is very small. It's infinite dimension, but the part which is uncontrollable is also infinite dimension. So that's interesting. Your question is very interesting because it's important to understand the case where the dimensions that you cannot control with the linearized control system, if it is of infinite dimension, what can be done? Yes.
Because I saw you have used some expansion, so it can be a second order or third order. It depends on the how much the missing directions space is, right?
Yes, you're right. Also, it may happen that the other two is not sufficient, the other three is not sufficient, and maybe any other could be not sufficient because it could happen that maybe for the other two you can have new direction, but a finite number of new direction also for the other three, and so on. So then it's going to be very complicated because you have to sum an infinite number of perturbation. Okay.
And just one more question regarding this phantom tracking method. So in the
Yes.
phantom tracking strategy, if we understand that the first one, whatever you show, there you have a parameter gamma. So
Yes, exactly.
without that gamma, you don't have any kind of stabilization results, right? So you introduce the gamma.
Yes. Well, that is without the gamma, if you consider the linear system, it's not controllable. So it's not so easy to stabilize it. But with the gamma, which is not zero, then the linear control system is controllable. So the linear control system around gamma, around the right point, is controllable. So you are sure that you are able to stabilize it by a feedback law, which is linear.
Yes, and then you gamma tending to zero.
Yes, and then the idea is to move also, to try to move also gamma to zero in the same way, with the same. In some sense, you want to move the point to the right point, but in some with some other method, you try also to move the right point to the green point. In some sense, it's like maybe it's better to, you see here, okay? If you look to 2, you want to, V is going to go to 0, okay? V is going to go to 0 for sure, but Y1 is going to go to what was called gamma, but gamma is V now. So Y1 is going to V, but V is going to 0, so Y1 is going to 0, and the same for Y2 and Y3.
So this one, when you show that the implicit Lyapunov, this implicit Lyapunov will give
Yes.
you only the local stabilization, because
exactly. Very, very interesting question. Yes, it's given only the local because it's given only locally, but using this type of improvements, that is instead of taking V of x, you take theta of V of x, and theta in some sense is small, but when you have V which is close to 0, theta of V is close to V, but for large value of V, it's let's say for example it's bounded and small, so then it's defined perfectly globally. It's defined globally. And then you have the same, that is V is going to converge to 0, theta of V is going to converge to 0 also, and then it means that x1 is going to 0, x2 is going to 0, x3, and there is no x4, sorry. So this is, you can also get, at least for the toy system, of course, for more general system, it can be much more complicated, but for this toy system, it's worked perfectly well, yes.
Okay, and this is the last, related to the last portion where you show the power series expansion with time varying feedback. If you can show the assumptions there, that is, you have x1 tilde and y tilde.
Yes.
Reverse.
Yes. Is this one?
Yes.
This slide?
So
Yeah.
here you assumption was there exists a control which is Lipschitz, and you
Yes.
have this kind of conditions from 0 to 0 first component. So what about the second component? It's 0. It does not go to the 0, right?
No. Yeah. You are perfectly right. The x is going from 0 to 0, while the y is going to 0 to something. Let's assume, for example, that capital L, the operator capital L is equal to 0. Okay. Then y tilde of t is not 0, but it has to satisfy y of t dot b is minus delta, which means in some sense that if you fix some b, it's possible to find a v which depends on b, such that for x you go from 0 to 0, while for y you move from 0 to something which is in the R space y of t dot b is less than minus delta. So you can move in all direction in some sense. You can move in all direction with this type of assumption. You can also, whatever is b, you can move in the direction of minus b in some sense.
And in that case, you're able to find the time periodic feedback law. That's all you're
Exactly. Yeah.
But in this situation also, it is not known. I think you mentioned that the stationary feedback law, there is a positive result or negative result, we don't know.
No, this is a very good question also. In the case that I present for the application, for example, in these three systems, the three systems, we know it's not possible to make it by a feedback which does not depend on time. We know it's not possible. Okay. But for the KTV equation, when we try to apply to the KTV equation, it's not clear if we cannot make it for with a feedback which is which does not depend on time. First, I should have mentioned maybe that if you just take u equal to 0, you get the convergence. It's asymptotically stable. You get the convergence to 0. but you do not get the exponential stability. You do not get 2. There is no, this inequality does not hold. If you just take u equals 0, you can show, in fact, that when you take u equals 0, for some critical lengths, it has not been done for all the critical lengths. This is something that I have done with Shuxia Tang and Jingsu Chu and Pepe Chang. We prove that the decay rate is like 1 divided by square root of t. It's not exponential. But if you use this feedback, you get a better convergence. And the open problem related to a question, is it possible to make it with a feedback which does not depend on time? Yes, it's a very interesting question.
Thank you.